that I started yesterday. Integration of rational expressions by partial fractions. Yesterday, I reviewed factoring, I reviewed long division, and I covered part one of this document, which is about decomposing a rational expression into a sum of simpler fractions. And we learned that there are three cases. Case one is when you have distinct product of linear factors at the bottom of the expression. Case two is when you have linear factors, but they have been repeated more than once. And case three is the case when you have a quadratic factor, which cannot be factored into linear ones. So you have an irreducible quadratic factor. And we learned how to decompose it into simpler fractions. Today, we're going to learn about how to integrate them after that. So there are these formulas here, but I really don't want you to think of them as formulas. Using just the methods that we have seen so far, like the basic formulas for antiderivative and substitution, you can easily find the antiderivative of this function. So I'm going to just show you one by one how it works. So if you have 1 over ax plus b dx, and you want to find the antiderivative of that, you can take u to be ax plus b, then du is going to be a dx, because the derivative of ax plus b is going to be a dx. Then you can easily multiply by 1 over a outside and by a inside. This will become 1 over a antiderivative of du over u. Yes, and we know that is 1 over a ln of absolute value of u plus c. And if you replace that u with whatever it is in terms of x, you get this. So I really don't expect you to use this as a formula. You would do a substitution. Same is true for the next one. If you have antiderivative of 1 over ax plus b to the power of 2 dx, you can take u to be ax plus b, du would be a dx, 1 over a integral of a dx. At the bottom you have ax plus b squared, and this becomes 1 over a integral of u to the power of negative 2 du, which you can then do by a formula. It's 1 over negative 1 u to negative 1 plus c, which I can also write as negative 1 over a 1 over u plus c. And if I replace the u with whatever it is, I get negative 1 over a times ax plus b plus c. So I get the next one. So as you can see, it's just a substitution. The third one, so if one of those partial fractions has this form, ax squared plus b at the bottom dx, that would be a simple substitution again. You take u to be ax squared plus b, then du would be 2ax dx, and you would be missing 2a in the numerator. So you can multiply by 2a on top, divide by 2a outside, and this becomes 1 over 2a integral of du over u, which is going to be ln of absolute value of u plus c. Last step, you can replace u with whatever u is, ax squared plus b plus c, and you're done. So you get the third one. Any questions so far? Okay, let's do the last one. For the last one, you have 1 over ax squared plus 1 dx. The right substitution is taking u to be root a x, and then du would be root a dx. That's the right substitution, because notice that I can write this as dx over root a x to the power of 2 plus 1, right? Then I can use this as the inner function. Take u to be root a times x. A is a constant, so du is going to be the derivative of this times dx. Now, I see that I am missing the root a on top. I divide by root a outside. I get 1 over root a. Integral of du on top. At the bottom, I have u squared plus 1. And for this, I have a formula. The antiderivative of this part is going to be arctangent. So the final answer is going to be 1 over root a arctangent of u plus c. Last step, I will replace u with this. So this is going to be 1 over root a arctangent of root ax plus c, as you can see here in the formula. So again, I want to emphasize, if I were you, I would not memorize any of these. I would just do a substitution, and that will give me the answer. So let's do some examples. Seven x plus 1 over x plus 3 times x minus 1. The indefinite integral of this rational expression. So 7x plus 1 is a rational expression that we worked with last class. It's this one. No, maybe not. So let's just do the decomposition. Your first step would be to decompose that, and I know that 7x plus 1 over x plus 3 times x minus 1 can be decomposed into the sum of two simpler fractions, where you have a over x plus 3 plus b over x minus 1. How do I know that? Because it's case 1. At the bottom of this rational expression, I have two distinct linear factors. That makes it case 1. So I need a over the first linear factor plus b over the second one. That is 7x plus 1 is equal a times x minus 1 plus b times x plus 3. Then x should be 1, x should be negative 3, and this will give me a and b. If I plug in 1, I'm going to get 8 is equal 4b. If I plug in negative 3, I'm going to get negative 21 plus 1 negative 20 is equal negative 4a. So that gives me b is 2 and a is 5. So that means this antiderivative can be written as a, which is 5 over x plus 3, plus b, which is 2 over x minus 1. That would be my first step. Then I have two simple fractions. I can easily find the antiderivative of these ones using a substitution, taking the denominator to be u. And if I do that, I can do this in my head. It's going to be 5 ln of absolute value of x plus 3 plus 2 ln of absolute value of x minus 1 plus c. And the reason I can do it in my head is that u is such that du and dx are going to be the same. If I take u to be x plus 3, then du is simply dx. So this is like having 5 over u du, which is going to be 5 times ln of absolute value of u. Make sense?
Just a question.
Yes.
We take for like each one, we take a different u, right? Like,
yeah. So I just want to do one of them for you here. Let's say you have integral of 5 over x plus 3. 5 over x plus 3 dx. You would take u to be x plus 3, then du is going to be dx. So this becomes integral of 5 integral of du over u, right?
yeah.
So it's going to be 5 times ln of absolute value of u plus c. It's going to be 5 ln of absolute value of x plus 3 plus c.
Yeah, what I meant, we redo this the same step on the other side, right?
For both of them, yes.
Yeah, okay, thank you.
For this one, that will give you the 5 ln of absolute value of x plus 3, and then you do it the same thing for this one. That will give you 2 ln of absolute value of x minus 1.
Okay, I understand. Thank you.
Good. Next example. Here you have another rational expression. It's a proper rational expression because the degree of the numerator is 2. The degree of the denominator is going to be 3 because you have the product of these 3 linear factors. X plus 3, x minus 1, and x minus 5 dx. I'm not going to spend any time on doing the decomposition because you already know how to do that. Yeah, this can be written as integral of a over x plus 3 plus b over x minus 1 plus c over x minus 5 because it's case 1. There are 1, 2, 3 linear distinct factors. And then you find a, b, and c. It's going to give you for a x plus 3, you'll get 2/3. Plus for b, you'll get 1 over 2, negative 1 over 2. And then for c, you get 5. So this is going to be 2/3 ln of absolute value of x plus 3 minus 1 over 2 ln of absolute value of x minus 1 plus 5 times ln of absolute value of x minus 5 plus c, and you're done. Okay, next one is case 2. It's case 2. How do I know? Because when I look at the denominator, I see one linear factor, which has been repeated only once, and then another linear factor, which has been repeated twice. I have integral 1 minus 3x over x to 3 plus 4x squared plus 4x dx. First, I can factor out x, get x squared plus 4x plus 4 dx. Then I factor this one more. I see that this is actually x plus 2 squared. So that makes it case 2. One linear factor, which has been repeated only once, the x, and then another linear factor, x plus 2, which has been repeated twice. That's case 2. So I know I can write this as a over x plus b over x plus 2 plus c over x plus 2 squared dx. Then I use the methods that we learned last class, and I find A will be 1 over 4 plus B will be negative 1 over 4, and then C will be negative 1 over 7. Sorry, negative 7 over 2. 1 over 4, negative 1 over 4, and negative 7 over 2. And then I can find the derivative, antiderivative of each one of them using a substitution. So this first one is going to be 1 over 4 ln of absolute value of x minus 1 over 4 ln of absolute value of x plus 2. And for this one, if I do a substitution, again, I'm doing it this in my head. I take u to be x plus 2. If I take u to be x plus 2, then dx and du are the same. So this becomes negative 7 over 2 over u squared times du. And that will give me plus 7 over 2 u to the power of negative 1, which I can also write as 1 over u plus c. I'm going to do this last one again for you, just do the substitution because I'm not sure it's absolutely clear for all of you. So if I want to do this, I have negative 7 over 2 x plus 2 squared dx. So this is the thing that I said I can do in my head. U is this, then du is dx. So this integral becomes negative 7 over 2 du over u squared, which is the same thing as having negative 7 over 2u to the power of negative 2 du, which is going to be negative 7 over 2 times 1 over negative 1 u to negative 1. So it's 7 over 2 u to the power of negative 1 plus c. And you can replace u with x plus 2 now, which is the same thing as this. So that's how you can do the last one. And again, I don't recommend doing it in your head. You can just write them down one by one, find the antiderivative, and that's it. But again, if you practice this enough, you'll be able to just write down the antiderivative. Are we good? Okay, next example. This is actually case 3. We have antiderivative of x minus 3 over x plus 2 times x squared plus 6. How do I know it's case 3? Because I have a combination of a linear factor, the x plus 2, and a quadratic one, x squared plus 6, which cannot be reduced. The x squared plus 6 cannot be reduced into a product of simpler linear factors. I can also check the delta. If I check the delta, I will see that for this quadratic polynomial delta, the discriminant is not a perfect square, which means that it is not factorable. So I know I can write this as a over x plus 2 plus bx plus c over x squared plus 6. Now, if I use the methods that we learned last class, I'm going to get a is negative 1 over 2 over x plus 2 plus this is going to be 1 over 2x plus 1 over 2 over x squared plus 6 dx. It's going to be like that. And then I can factor out the 1 over 2. I get negative 1 over 2 integral of 1 over x plus 2 plus 1 over 2 integral of x plus 1 over, yeah. It's just, there's no 1 over 2 here. Factor out the 1 over 2, you get x over x squared plus 6 dx. Actually, c is going to be 0. C is going to be 0, and of course, I'm not doing this in my head. I just use this. So C is 0. Next step, yeah? Question?
It's 1/2 times antiderivative of what over x
Oh,
squared?
yeah. This, I see my board is acting up.
Okay.
So let me just rewrite that. It's going to be 1 over x plus 2 plus 1 over 2 antiderivative of x over x squared plus 6 dx. It's going to be like that. So forget about this. So this 1 over 2 here, you can just move it to the front. You can just move it out of the integral because it's a constant. Okay, then. Now, next I need to find the antiderivative of each one of them. The first one, so antiderivative of negative 1 over 2 over times 1 over x squared plus 1 dx. This one is going to be negative 1 over 2 ln of absolute value of x plus 2. And the other one, you have 1 over 2 antiderivative of x over x squared plus 6. I can take u to be x squared plus 6, then du is going to be 2x dx. So I am missing a 2. So I multiply by a 2 and I divide by a 2. Now this becomes 1 over 4 antiderivative of du over u. So it's going to be 1 over 4 ln of absolute value of x squared plus 6, like this. So the final answer is going to be negative 1 over 2 ln of absolute value of x plus 2 plus 1 over 4 ln of, I'm not going to put this in absolute value because x squared plus 6 is always positive. It doesn't really matter if I put absolute value or not. Yeah, so here you have absolute value, but x squared plus 6 is always positive. You agree? X squared is always positive. 6 is also always positive. If you add up two positive numbers, this is always positive. It can never be negative. So you can just let go of the absolute value. It will still be correct. Any questions? Okay, then let's do the last example. Integral of x squared plus 4x minus 7 over x minus 3 times x squared plus 6x minus 6 dx. It's not obvious that this is case 3. Yes, I know it's case 3 because I'm looking at this, but it's not obvious just by looking at this that this is case 3, because the first question that comes to mind is that, can I factor this more? Maybe I can break it into two simpler factors. Let's just check the delta. B squared minus 4ac. That's 6 squared minus 4 times a times c. That's going to be 36 plus 24, which is 60. okay, this is not a perfect square. And since 60 is not a perfect square, then for sure this is not factorable. So we're dealing with a linear factor and an irreducible quadratic one. So that means I can write this as a over x minus 3 plus bx plus c over x squared plus 6x minus 6 dx. If I find a, b, and c, I'm going to get this. I'm going to get, apparently a is 2/3 over x minus 3 plus x squared plus 6x minus 6. You're going to find 1/3 for b, and you're going to find 1 for c. Plus 1. If I multiply them back, I get 1/3 times x. 1/3 times 3 is 1 dx. And the step after that would be what we have over here. You can just bring that 2/3 out, and you can factor out a 1/3. If you factor out a 1/3, on top you get x plus 1/3. Make sense? Because 1/3 times you're gonna get, you're gonna get 3. Because 3 times 1/3 is going to be 1. That is, if you multiply back this and this, you get 1/3x. And if you multiply 1/3 and 3, you get the 1 over here. Next step, you use substitution. So since I have it over here, I'm going to erase the board. Any questions so far? Derivative of 2/3, 1/x minus 3 dx is going to be 2/3 ln of absolute value of x minus 3. And antiderivative of 1/3 x plus 3 over x squared plus 6x minus 6. I'm going to take this to be u. U is x squared plus 6x minus 6. Then du is going to be 2x plus 6, which I can write as 2 times x plus 3 dx. So you see I have the x plus 3 times dx here on top. What I am missing is multiply that by 2. So 2, 2. 1/6. du on top. Everything here is du over u. So it's 1/6 ln of absolute value of u plus c, where u is this, x squared plus 6x minus 6 plus c. So the final answer is going to be this plus c. So you're going to practice a lot of substitution in doing these exercises. So we had no example like this one. So I'm going to do one, just make up one thing, one example. If you have something like this, let's say 5x squared plus 1 dx. How can you find the antiderivative of that? In this case, you're going to end up with arctangent. So you can write this as 1/√5x, that to the power of 2 plus 1 dx. Then take u to be root 5 x, so that du is root 5 dx. Then you realize that you have the dx, you don't have the root 5, so you can multiply by root 5 here and divide by root 5 outside. This becomes 1 over root 5, antiderivative of du on top, u squared plus 1 at the bottom, which is going to be 1 over root 5 arc tangent of u plus c. So last step, replace u with whatever u is in terms of x. So if one of your partial fractions has this form, you will use this substitution. Okay, so before I let you work on the exercises, I want to talk about part C because I've already covered this. Last class, we talked about long division, and I promised to give you more examples. So this is it. If you're dealing with an integral of a rational expression where the numerator has a degree higher than the denominator, like here you have 3x cubed plus 8x squared minus 10x plus 15. So the highest degree here is 3. At the bottom, you have x plus 4. So it's linear. The degree is 1. That would be an improper integral, improper rational expression. In the case of an improper rational expression, what you need to do is long division. So 3x to the power of 3 plus 8x squared minus 10x plus 15. That's my dividend. I divide that by x plus 4. So what do I multiply by x to get 3x cubed? 3x squared. Then I multiply this by this. I get 3x cubed plus 12x squared. Put braces around these. These two will cancel. I'm going to be left with 8x squared minus 12x squared. That's minus 4x squared minus 10x plus 15. Next, I need to repeat the same process. Multiply, what do I multiply by x to get negative 4 x squared? And the answer is minus 4x. Multiply this by the whole divisor, minus 4x squared minus 16x. Put that inside brackets, subtract. These two will cancel. I'm going to get 10x minus 16x. That's negative 10x plus 16x. That's positive 6x plus 15. I'm going to repeat this process because my remainder is not yet of a lower degree than my divisor. So I need to repeat this. I need a plus 6 here. 6 times x, 6x, plus 6 times 4, 24. Subtract, you're going to get 15 minus 24 minus 9. So that means this fraction here, it can be written as the quotient, which is this, plus the remainder, which is this, over the same divisor, which is this. And this is what you see here, over here. This is the quotient, 3x squared minus 4x plus 6. Then you can have a plus minus 9 here over the divisor. And then you see it's very easy to find the derivative now, the antiderivative now. Antiderivative of this part is 3 over 3x cubed. Antiderivative of this part is minus 2x squared. Antiderivative of this part is simply 6x minus antiderivative of this part is going to be 9 ln of absolute value of x plus 4. Example, the rest of the examples are all the same. It needs long division. So here, when you do the long division, you're going to have 2 as the quotient and 2x plus 5 as the remainder over this divisor. Yes, and the divisor can be factored more. So for this problem, the improper rational expression becomes 2 plus 2x plus 5, which is the remainder over x squared plus x minus 6. Now this one is a proper one, and you can use the methods that we learned in part A to decompose this fraction into simpler fractions. And if you realize that this is case 1, because the bottom can be factored into x plus 3 and x minus 2. Then you know that you can write this as 2 plus a over x plus 3 plus b over x minus 2. Then you find a and b and the rest of the story. Is this clear? Do you need to see more examples of long division, or you're good with that? Okay, so I'm going to just assume that you know how to do that. After you do the long division for this one, you're going to get 2 plus, this would be your remainder, 40 minus 11x over, first you factor out, you have x to the power of 3 plus x squared minus 20x. You can factor out 1x, you get x squared plus x minus 20. Then you factor more, you get x plus 5 and x minus 4. Because the sum is supposed to be 1 and the product is supposed to be minus 20. And again, this would be case 1, because at the bottom you have 1, 2, 3 distinct linear factors. You would be able to write this fraction, 40 minus 11x over x times x plus 5 times x minus 4. You would be able to write that as a over x plus b over x plus 5 plus c over x minus 4. Then you find a, b, and c. It's going to be like that. And then finding the antiderivative of each one is very easy. Last example. This one is going to be type 2 or case 2, because when you do the division, you're going to get 2x plus 3 as your quotient. You get 9x squared minus 35x minus 6 as your remainder. At the bottom, you have this divisor. And this divisor, if you factor it, it's going to be this. I'm going to show you how to factor that one. You have x to 3 minus 6x squared plus 9x. Factor out x, you get x squared minus 6x plus 9. You realize that this here follows the pattern a squared minus, follows the pattern a squared minus 2ab plus b squared. This is just a minus b squared. If you see the pattern a squared plus 2ab plus b squared, that would be a plus b squared. Now this is just x minus 3 squared. X squared, that's the a squared. 3 squared, that's the b squared. And here you have minus 2 times 3 times x, minus 6x. So that makes it case 2, because you have one linear factor which has been repeated once and another one which has been repeated twice. So I know that this 35x minus 6 over x times x minus 3 to the power of 2 can be written as a over x plus b over x minus 3 plus c over x minus 3 squared. Then I find a, b, and c. And after that, I just use substitution to find the antiderivative of each part. Are we good? Okay, so I want you to work on these exercises from part B and part C. All the exercises here in part B, they are proper rational expressions. That is, the degree of the numerator is the numerator is less than the degree of the denominator. That is, for these ones, you will not need to do any long division. And for all the problems, all the exercises here in part C, these are improper rational expressions. That is, the degree of the numerator is either the same or more than the degree of the denominator. So you will have to begin with a long division, and then you are here. Then you have to solve an equation, an antiderivative like these ones. These they come with solutions. So start working on these problems. Compare your solution with the solution provided in the notes. If you don't understand something, let me know.